Hello guys, welcome to my channel Pen and Pencil. Today we are going to learn Chapter 4 Atomic Structure of Class 8 Chemistry. So before starting the topic, please subscribe my channel and also like, share and comment. Topic Atomic Structure. Let's start. Atomic structure. Introduction. What is the smallest particle you can think of? Do you think you can break it down to even smaller particles? In the previous lesson, we studied that the atom is the smallest unit of an element. In this chapter, we will look at what atom is itself is made of. We know that different elements have different properties. What is it that makes elements behave differently? Is it the atom or what lies within the atom? Atoms. If we could keep splitting an element until the smallest unit that cannot be split further is reached, we would get atoms. An atom is the smallest particle of an element. Every atom of an element exhibits all the properties of the element. There is a limit to how small a chunk of matter can be broken down to using simple tools. Advanced equipment can break it down to a very fine powder. Extremely sophisticated equipment and extreme conditions are required to break the particles in the fine powder to the size of an atom. Atoms are so small that they cannot be seen with naked eye. We know of their existence based on experiments. Scientists, while experimenting with elements, have detected the pressure and presence of atoms. Now, the history of atoms. Kanada's Paramanu. Acharya Kanada was an Indian philosopher who lived sometime between the 6th and 22nd century BCE. He put forward the idea of a particle that could not be derived any further. He called this indivisible particle the Paramanu. Kanada proposed that the Paramanu cannot be seen with the naked eye. His prediction was proved right by scientists centuries later. After the advent of scientific experimentation, Kanada recorded his ideas in the Vaisaka Sutra. Theory of the universe. Democritus, a Greek philosopher who lived in 400 BCE, predicted the presence of atoms. According to his theory, if a piece of matter is divided until it could be divided no further, a fundamental or basic unit would be reached. Democritus called this fundamental unit an atom. He called his theory the theory of the universe as it covered all matter. Now, John Dalton's atomic model. John Dalton was an English chemist, physicist, and meteorologist. In 1809, he proposed the atomic theory, which was an important milestone in the history of science. He postulated that, point number 1, all matter consists of small indivisible particles called atoms. Atoms can neither be created nor be destroyed. All the atoms of an element exhibit identical properties. However, atoms of one element differ from the atoms of other elements. When elements react, their atoms combine in simple whole number ratios to form compounds. For example, one atom of carbon combines with two atoms of oxygen to form carbon dioxide, CO2. During chemical reactions, atoms of the reactants do not change. They only get rearranged to form the products. Though Dalton's theory explained numerous experimental observations, it could not answer one big question. What was the atom itself made of? The answer to this question was obtained after decades of research. Now, the discovery of electron. In 1879, William Crookes, a British scientist, first observed the electron. He performed experiments in a glass tube from which air had been removed. He placed metal plates called electrodes at the both ends of the tube. The negatively charged electrode is the cathode and the positively charged electrode is the anode. Point number 1. Very high voltage was applied across the tube. A beam flowed from the cathode to the anode. This beam was called a cathode ray and was believed to contain negatively charged particles. The cathode rays were invisible to the naked eye and could be seen only with the help of a special screen called a phosphorescent screen. When the ray struck the screen, a dot appeared on it. J. Thomson, an English physicist, studied the properties of the cathode rays and made some important observations. He was awarded the Nobel Prize in Physics in 1906. Point number 1. The cathode rays always traveled in straight lines. However, when charged plates were placed around the tube, the rays were deflected away from the negative plate and towards the positive plate. This suggested him that the cathode rays contained particles with a negative charge. The beam cast the shadow of a fan placed in its path, suggesting that it traveled in a straight line. The mass of each particle in the cathode ray was more than 10 times lighter than a hydrogen atom. Thomson predicted that these particles should have come from within the atom, and he called them corpuscles. Later, they were renamed as electrons. Electrons were the first subatomic particles to be discovered. The charge of electron was measured by R. Millikan in his oil drop experiment. He determined the charge of an electron to be minus 1.60 into 10 to the power minus 19 coulombs. The mass of an electron was found to be 9.1 into 10 to the power minus 28 gram, which is so less that it is considered to be negligible. Now, plum pudding model of the atom. On the basis of his discoveries, Thomson predicted what an atom would look like. He said that each atom is like a sphere filled with a fluid of positive charge. The negatively fluid corpuscles are suspended in this fluid. This resembles plums suspended in a sticky pudding, and hence the unusual name for this model. Now, the discovery of the nucleus. Discovery of the nucleus. Ernest Rutherford was a scientist born in New Zealand who was awarded the Nobel Prize in Physics for his work in nuclear physics. He worked under the guidance of J. Thomson. In 1910, he performed his famous gold foil experiment. Rutherford set up an experiment where positively charged particles were fired at a very thin foil in an evacuated chamber. A circular fluorescent screen was placed behind the gold foil to detect the alpha particles. He observed the following. Most of the particles went through the foil in a straight line without being deflected. A few particles passed through the foil and were slightly deflected. Occasionally, a particle bounded back. Based on these observations, Rutherford concluded the following. Since most of the alpha particles went straight through the foil without being deflected, the atom must consist a lot of empty space. A positively charged mass in the atom caused some of the alpha particles to be deflected due to repulsion. As only a very few particles bounced back, the positively charged mass in the atom is very small, heavy, and is located somewhere at the center of each atom. He called this mass the nucleus. Now, Rutherford's planetary model of the atom. Based on his findings, Rutherford postulated that an atom has a nucleus at its center, which is a dense mass of positively charged particles. The electrons moved around the nucleus. Rutherford compared this model of the atom to a mini solar system where the nucleus is like the sun and the electrons are like the planets that orbit the sun. Scientists were quick to point out a flaw in the model. As positive and negative charges attract each other, what prevented the electrons from falling into nucleus? Now, the Bohr's atomic model or Rutherford-Bohr model. Niels Bohr, a Danish physicist, also worked under the guidance of J.J. Thomson. He agreed with the planetary model of the atom. However, he defined this model by stating that each electron would move only in a specific path around the nucleus called an orbit. Electrons can move to a lower or higher orbit only by losing or gaining energy. This model addressed the flaw in Rutherford's model. In 1922, Niels Bohr received the Nobel Prize in Physics for his work on the structure of atom. In due course, it was discovered that the nucleus of an atom was made up of two kinds of particles, protons and neutrons. The proton was first observed by Goldstein and was named by Rutherford. A proton is positively charged particles and weighs as the same as the hydrogen atom, the lightest atom, that is 1.67 into 10 to the power minus 24 grams. A proton carries a single positive charge of 1.60 into 10 to the power minus 19 coulomb. The charge is equal and opposite to that of an electron. The mass of the proton is 1836 times greater than that of electron. The neutron was discovered by James Chadwick in 1935 and was awarded a Nobel Prize in Physics for this discovery. A neutron is an uncharged or neutral particle with about the same mass as a proton. Hence, within the atom, there are three different types of particles, smaller than the atom itself. They are electrons, protons, and neutrons, and are together called fundamental particles or subatomic particles. In the above table, the mass of the particles is given in atomic mass units AMU, where 6.022 in 10 to the power 23 AMU equals to 1 gram G. Now, the structure of atom. The mass of an atom is concentrated in the nucleus. The nucleus of an atom is positively charged. The nucleus contains two different kinds of particles, neutrons and protons, held close together. A third kind of particle called electrons moves around the nucleus. For an atom to be electrically neutral, the number of electrons in the atom must be equal to the number of protons. This number is called the atomic number and is different for each of the 118 elements in the periodic table. The atom's number is the number of protons present in the atom. It is unique for each atom and is represented by the unique symbol Z. No two elements can have the same atomic number. The number of neutrons present in the nucleus is around the same as the number of protons present. The neutrons do not affect the charge of the nucleus as they are neutral. However, they add to the mass of the nucleus and therefore of the atom. A neutron has about the same mass as proton, that is 1 AMU. More than one element can have the same number of neutrons. The mass number of an atom is the sum of the numbers of protons and neutrons present in the nucleus and is represented by the symbol A. The atomic mass of an atom is calculated in AMU and is close to the mass number. It is obtained by adding the masses of the protons and the neutrons present in the nucleus. Since the mass of the electron is negligible, it is ignored. The atomic number and the atomic mass of each element are given in periodic table. The atomic number is written above the symbol and the atomic mass is given below the symbol. The mass number is the nearest whole number to the atomic mass. An element is often represented as a symbol with the mass number as a superscript and the atomic number as a subscript. Let us see how many common elements can be represented in this method. Characteristics of atoms. Point number 1. The number of protons in an atom is unique to each atom and is what distinguishes the atom of one element from that of another. It is called the atomic number and is represented by the letter Z. The number of electrons in an atom is always equal to the number of protons, so that the atom as a whole is neutral. The mass of the atom is concentrated in the nucleus, which contains protons and neutrons held together strongly. The total number of protons and neutrons in an atom is called a mass number and is represented by the letter A. The number of neutrons in an atom can be obtained by subtracting Z from A. The electrons move around the nucleus in specific orbits. They take part in chemical and physical changes. The properties of an element depend on the number and orientation of the electrons in the atoms. The size of the nucleus is much smaller than the size of the atom. If the atom is imagined to be the size of the football field, the nucleus would be only the size of the mosquito. Example 1. The atomic number of bromine Br is 35 and its atomic mass is 79.904. What is the mass number of Br? What are the numbers of protons, electrons, and neutrons in the atom of Br? Based on given information, number of protons is equal to atomic number is equal to 35. Number of electrons is equal to number of protons is equal to 35. Mass number is equal to atomic mass rounded off is equal to 80. Number of neutrons is equal to A minus Z is equal to 80 minus 35 is equal to 45. More than one element can have the same number of neutrons. As atomic number is unique property of each element, the elements in the periodic table are arranged in order of increasing atomic number. Now we will study isotopes. The number of protons is unique to an element, but the number of neutrons in an element can vary. Note example, carbon has 3 different types of atoms with different numbers of neutrons. Atoms of the same element with different number of neutrons but the same number of protons are called isotopes. They have similar chemical properties but differ in their physical properties. A variation in the number of neutrons does not affect the charge of the nucleus, as neutrons are neutral. However, the atomic mass of each isotope will be different. Some examples are given below. Carbon has 3 isotopes: carbon 12, carbon 13 and carbon 14. The number following this name indicates the mass number of the isotope. Carbon 12 is more abundant in nature. Chlorine has 2 isotopes. Chlorine 35 has 18 neutrons and 17 protons, while chlorine 37 has 20 neutrons and 17 protons. Chlorine 35 is more abundant than chlorine 37. Hydrogen has 3 isotopes. Hydrogen are protium, deuterium and tritium. Their mass numbers are 1, 2 and 3 respectively. Protium is the most abundant of the 3 isotopes. Example number 2. The 3 isotopes of lithium are Li 6 to the power 3, Li 7 to the power 3 and Li 8 by 3. What are the numbers of protons and neutrons in each? Solution. Isotopes of an element have the same number of protons. Hence, all the lithium isotopes have 3 protons. They differ in the number of neutrons, which is calculated by A to Z or A minus Z. Hence, the 3 isotopes have 3, 4 and 5 neutrons respectively. Now, the electronic configuration. The arrangement of an electrons in an atom of an element is called the electronic configuration of the element. The study of the atoms by Niels Bohr and others has shown that electrons move around the nucleus in fixed paths called orbits. They cannot move randomly. Each orbit corresponds to a certain energy level. If an electron has to move to an orbit or level closer to the nucleus, it has to lose some energy. If an electron has to move to an orbit or level farther from away the nucleus, it has to gain some energy. The levels are also called shells and are named as K, L, M and N and so on. The maximum number of electrons in each level is equal to 2n square, where n is the shell number. K shell. Hydrogen has one electron which occupies the K shell. Helium has two electrons and both occupy the K shell. The K shell can accommodate a maximum of two electrons. These two elements have their outermost electrons in the K shell. L shell. Lithium has three electrons. Since the K shell has a maximum capacity of two electrons, the third electron moves to the L shell. As the atomic number increases from lithium to neon, each successive electron occupies the remaining space in the L shell. At neon, the L shell gets fully occupied with the maximum number of 8 electrons. These 8 elements have their outermost electrons in the L shell. M shell. Sodium has 11 electrons. The first 2 electrons occupy the K shell. The next 8 occupy the L shell. And the 11th electron enters a new shell, the M shell. As the atomic number increases from sodium to argon, each successive electron occupies the remaining spaces in M shell. The argon, the M shell, has 8 electrons. These 8 elements have their outermost electrons in the M shell. Beyond argon, the occupation of the electronic levels gets more complex. The electrons in the outermost level of an atom are the reason why animal reactions take place. The inert and noble gases, helium, neon, argon, and so on, are very stable and unreactive. This is because they have completely filled outer electronic shells, 2 electrons in the case of helium and 8 electrons in the other noble gases. Such configurations are very stable and called octet or duplet in case of helium configurations. Now, valency. Atoms combine with each other to form molecules. If the atoms in a molecule are identical, it is an element. If the atoms are different, it is a compound. The tendency of an atom to combine with another atom to form a molecule depends on the number of electrons in its outermost shell. The outermost shell of an atom is called the valence shell, and the electrons present in the valence shell are called valence electrons. Now, the electronic configuration and valency. An atom with a completely filled valence shell is highly stable. We have already seen that noble gases are very stable due to their completely filled valence shells. Helium has 2 valence electrons. The maximum capacity of the K shell is 2, while all other noble gases have 8 electrons in their valence shells. Atoms with incomplete valence shells combine with other atoms in order to complete their valence shells or achieve the electronic configuration of the nearest noble gas. This is called the octet or duplet rule. Hydrogen, the first element in the periodic table, has 1 valence electron in the K shell and is very reactive. It combines with all nonmetals and some metals to form compounds. In order to attain the stable electronic configuration of the nearest noble gas, helium, hydrogen must gain 1 electron. The valency of an element is the number of hydrogen atoms that can combine with or replace one atom of the element. It is also the combining capacity of an atom. Hydrogen can gain 1 electron to complete its K shell in 2 ways. In both these ways, molecules are formed. Now, the sharing of electrons. Sharing of electrons. Hydrogen chloride molecule. The formula HCl shows that 1 atom of chlorine combines with 1 atom of hydrogen. Hence, the valency of chlorine is 1. The hydrogen atom has an electronic configuration of 1. The chlorine atom has an electronic configuration of 2, 8, 7. The hydrogen atom needs 1 electron to complete its outermost level and become stable. The chlorine atom needs 1 atom to obtain a stable octet configuration. This can be achieved if they share 1 electron between themselves. The atoms have to come close to each other and their valence shells have to overlap so that the electron sharing can occur. The electron from hydrogen completes the octet for chlorine. The electron from chlorine completes the duplet for hydrogen. By sharing of an electron, hydrogen and chlorine form a bond. It is represented by a long dash between the hydrogen and chlorine and is called a single bond or covalent bond. A covalent bond is formed between atoms by the sharing of electrons in their outermost electronic level. The resulting compound is called a covalent compound. Water molecule, the formula H2O shows that one atom of oxygen combines with two atoms of hydrogen. Hence, the valency of oxygen is 2. The hydrogen atom has an electronic configuration of 1. The oxygen atom has an electronic configuration of 2, 6. The hydrogen atom needs one electron to complete its outermost shell to become stable. The oxygen atom needs two electrons to complete its valence shell and become stable. This can be achieved if two hydrogen atoms share an electron each with oxygen as shown below. Outermost electrons from two hydrogen atoms complete the valence shell of oxygen. Two different electrons from oxygen complete the valence shells of two hydrogen atoms. The three atoms, namely two hydrogen atoms and one oxygen atom, have to come close to one another for their valence shells to overlap. The water molecule has two single bonds, one to each hydrogen atom, form the oxygen atom. Ammonia molecule. The formula NH3 shows that one atom of nitrogen combines with three atoms of hydrogen. Hence, the valency of nitrogen is 3. The hydrogen atom has an electronic configuration of 1. The nitrogen atom has an electronic configuration of 2, 5. The hydrogen atom needs one electron to complete its outermost level. The nitrogen atom needs 3 electrons to complete its outermost level and become stable. This can be achieved if their hydrogen atoms, 3 hydrogen atoms share an electron each with nitrogen. Outermost electrons from 3 hydrogen atoms complete the outermost level of nitrogen. 3 different electrons from nitrogen complete the outermost levels of the 3 hydrogen atoms. The 4 atoms, namely 3 hydrogen atoms and 1 nitrogen atom, have to come close to one another for their outermost electronic levels to overlap. The ammonia molecule has 3 single bonds, one to each hydrogen atom from the nitrogen atom. Methane molecule. The formula Ch-4 shows that one atom of carbon combines with 4 atoms of hydrogen. Hence, the valency of carbon is 4. The hydrogen atom has an electronic configuration of 1. The carbon atom has an electronic configuration of 2, 4. The hydrogen atom needs one electron to complete its outermost level and become stable. The carbon atom needs 4 electrons to complete its outermost level and become stable. This can be achieved if 4 hydrogen atoms share an electron each with carbon. Outermost electrons from 4 hydrogen atoms complete the outermost level of the carbon. 4 different electrons from carbon complete the outermost levels of 4 hydrogen atoms. The 5 atoms, 4 hydrogen and 1 carbon, have to come close to each another for their outermost electronic levels to overlap. The methane molecule has 4 single bonds, one to each hydrogen atom from the carbon atom. Loss or gain of electrons. Sodium hydride. From the formula NaH, we see that one atom of sodium combines with one atom of hydrogen. Hence, the valency of sodium is 1. The hydrogen atom has an electronic configuration of 1. The sodium atom has an electronic configuration of 2, 8, 1. If the hydrogen atom gains 1 electron, it will have a complete outermost level and become stable. The sodium atom needs 7 electrons to reach an octet configuration of 8 electrons in its outermost level M shell and become stable. It is difficult to obtain 7 electrons. However, if the sodium atom loses 1 electron from the outermost level M shell, it would be with a stable octet configuration in the new outermost level L shell. The lost electron could be gained by a hydrogen atom. Let us see how this happens. In the figure above, we can see how the outermost electron of sodium is lost completely and the hydrogen atom accommodates this electron in the outermost level. Sodium now has a stable octet configuration of 8 electrons in its outermost level and hydrogen has a completely filled outermost level. Both atoms are now stable. However, the sodium atom has now a net positive charge having lost one electron and the hydrogen atom has a net negative charge having gained an electron. They are called ions as they carry charges. The ion with a positive charge is called a cation. The ion with a negative charge is called an anion. Since opposite charges attract each other, the sodium ion and hydride ion stay bound to one another. This kind of bond is known as ionic bond, and the resulting compound sodium hydride is an ionic compound. An ionic bond is formed between a metal and non-metal by the donation of electron from the outermost level of the metal to the outermost level of the non-metal. By the gain or loss of an electron, an atom becomes a charged particle or ion. Ions are held together by strong attractive forces. The compound thus formed is called ionic compound. Magnesium hydride is from the formula MgH2. We see that one atom of magnesium combines with the two atoms of hydrogen. Hence, the valency of magnesium is 2. The hydrogen atom has an electronic configuration of 1. The magnesium atom has an electronic configuration of 2, 8, 2. The hydrogen atom needs 1 electron to become stable. The magnesium atom needs 6 electrons to reach an octet configuration of 8 electrons in its outermost level M shell and become stable. It is difficult to get 6 electrons. However, if the magnesium atom loses 2 electrons in its M shell, it will be left with a stable octet configuration in the new outermost level L shell. At the same time, the lost 2 electrons could be gained one each by 2 hydrogen atoms. Let's see how this happens. From the outermost level of magnesium, 2 electrons are lost completely and 2 hydrogen atoms gain 1 electron each in their outermost levels. Magnesium now has a stable octet configuration of 8 electrons in its outermost level and the 2 hydrogen atoms have stable duplet configurations. All 3 atoms are now stable. However, the magnesium atom has 2 positive charges having lost 2 negative charges and each hydrogen atom has a net negative charge having gained an electron each. Since opposite charges attract each other, the magnesium ion and hydride ion stay bound to one another, forming a molecule of magnesium hydride. The valency of elements can also be found from compounds formed with oxygen or chlorine. The valencies of an oxygen and chlorine have already been determined as 2 and 1 respectively as they form compounds H2O and HCl with hydrogen. For example, barium and chlorine combine to form barium chloride BaCl2 since the valency of chlorine is 1. The valency of barium must be 2. Silver forms an oxide Ag2O and the valency of oxygen is already known as 2, so the valency of silver must be 1. Now, variable valency. Some elements exhibit variable valency. For examples, iron has valencies of 2 and 3. The suffix "ous" is used to indicate the lower valency and the suffix "ik" is used to indicate the higher valency. Non-metals such as nitrogen, phosphorus, and sulfur also exhibit variable valencies. Nitrogen has valencies of 3 and 5, phosphorus has valencies of 3 or 5, sulfur has valencies of 2, 4, or 6. Relationship between the valency of elements and the periodic table. The first 20 elements in the periodic table are listed with their names, symbols, and valencies derived from observing their combining capacities. It reveals an interesting pattern. You can see that the valency of elements increases from 0 to 4 and then decreases from 4 to 0. Let us now see how this pattern can be explained. Now, the periodic table. Mendeleev, the Russian chemist, derived this wonderful tool to illustrate the physical and chemical properties of the elements and relationship with one another. He placed the elements in a compact table called the periodic table. The elements are arranged in increasing order of the atomic numbers. The periodic table has 18 columns and 7 rows. The rows are called periods and the columns are called groups. Columns 1 and 2 are 13 to 18 are numbered in Roman numerals as 1a to 8a. The columns in the middle are numbered from 1b to 8b, but we will not take up that now. In the first 20 elements in the table, you will observe the following. Elements H, L, I, Na and K with valency 1 are found in group I1a. Elements B, Mg and Ca with valency 2 are found in group 2a. Elements B and Ai with valencies 3 are found in group 3a. Elements C and Si with valency 4 are found in group 4a. Nitrogen and phosphorus exhibit valency 5 in addition to valency 3 and are hence placed in group 6a or 5a. Sulfur in group 6a exhibits valency 6 in its natural form S to the power 6. Elements He, Ne and Ar with valency 0 are found in group 8a. Group 8a is also referred to as zero group as the elements in this group are inert or unreactive and have valency of 0. Thus, elements with same valency have been placed in the same group in the periodic table and their chemical properties are found to be similar. From the periodic table, we should be able to find the valency of any element. So guys, today's video ends here as the chapter is completed. So, thank you guys.